To start off our lesson about subspaces, we need a couple of definitions. So we'll define what it is to be a span of a set of vectors, and then also talk about how we can describe a set of vectors, or how we can describe the span of a set of vectors using some of the notation that we are familiar with. And then we'll also take a look at the null space and the range of a matrix as well in this lesson. So let's just talk about what the span is first. And we'll have a couple ways to think about this when we start getting into matrices in the later part of this lesson as well. So the span of a set of vectors, and we'll take a set here S to be V1 through Vn as our set of vectors. And this is going to be out of some space Rn. Then the span is the set, or subset rather, generated by taking all linear combinations of those vectors. The vectors in the set S. And we denote it as the span of S, or if we want to list all the vectors, the span of the set V1 up to Vn. And we get a theorem out of this. We consider a subset or collection of vectors W that's in Rn, then the set of all linear combinations of the vectors in W form a subspace. So in our case, we use the letter S to denote our collection of vectors, but either way, the conclusion is that automatically the space generated by the span of these vectors will then be a vector space, so it gets termed as a subspace. So that's theorem 3 in your text, and if you want to look up the proof, you can see it there. Just a little bit more terminology that can go along with this. If S is our set of vectors, the subset, or subspace rather, W consisting of all linear combinations is called the subspace spanned by S and is denoted by these two different ways of writing it. So just a little bit different way to talk about what that space looks like. So let's look at an example. And this is a very simple example. We'll just take a single vector and we'll look at its span. So we'll just let this vector be 1, 2, 3. So that's our only vector in our subset here. Then the span is the linear combinations of that. Then the span of our vector v is going to be equal to all linear combinations of our vector 1, 2, 3, and I'll just use t as a scalar, such that t is an element of the reals. Again, that's all linear combinations of that vector. So what that tells us, if we just multiply those two things up, is that if we take x equal to t, y equal 2t, and then z would be equal to 3t, what we have is geometrically here a line in R3. So that's a pretty simple example, but not very interesting because it's only one vector. And if we take linear combinations of one vector, we always get a line geometrically, which is good to know. But let's look at something a little bit more interesting here. And we'll take a look at a set of two vectors. So here's another example. We'll take a vector u to be equal to 3, 1, 4. And another vector v to be our same 1, 2, 3. And now let's talk about the span of these two. So the span of u and v. Which again is all linear combinations of these two vectors. Which, when written out, would look something like this. And I'll use x1 and x2 this time as our variables. So it's the set of all things y, x1 times our first vector, 3, 1, 4, plus x2 times our second vector, 1, 2, 3, where x1 and x2 are elements of the real numbers. So we're looking again at linear combinations of these two vectors now. And y is also going to be an output in R3. So y1, y2, y3. And what we're after here is trying to devise some way to describe what the set of all outputs need to look like. We can liken this to the range of these vectors as well in some regard. So we get a subspace that's generated by these two vectors, and that subspace that we get can be thought of as the range. It's the set of all outputs from this particular matrix, or from this particular set of vectors, rather. So continuing down, if we start thinking like we might have to solve a system here a little bit, we would take this and rewrite a system of equations like y1 equals 3 times x1 plus x2. Our second row would look something like y2 is going to be equal to x1 plus 2x2. The third row would be y3 being equal to 4x1 plus 3x2. So now this is looking like a system. And if we flip it around, although we necessarily don't have to do that, I think it helps reveal what we're supposed to do to continue the process. So then we have x1 plus 2x2 equals y2, and 4x1 plus 3x2 equals y3. Again, what we're after is a description for the set of all outputs here. How do we sort of describe, if we're thinking from a functional standpoint, how do we describe the range of all of these things? And that would be the output side, these y values. So it seems like I've got a system of equations that could be solved here, and it looks like we would throw this into an augmented matrix. So if we do that, we would have a matrix that looks like 3, 1, 4, 1, 2, 3, and we can augment it then with our outputs y1, y2, and y3. And then we would row ref it. So now we're at a place where using our octave won't help us out because we've got variables sitting in here. So we have to go back to solving this by hand. And I'll include maybe a detailed solution on that work as an additional handout. But if we do that, this is what we get. So then you would have y2. You get 3/5 y2 minus 1/5 y1. And in the bottom row, minus y1 minus y2 plus y3. And it's this bottom row that is of the most interest to us. We have consistent relationships in rows 1 and row 2, but in row 3, the only way that we get a consistent relationship here is that if this particular expression is equal to 0. So that becomes our condition that we apply to finish solving out the problem. So for the system to be consistent, we must have minus y1 minus y2 plus y3 be equal to 0. And that now becomes our condition. And if we want to multiply that through by a -1, that just kind of makes it look, I guess, a little bit better. Plus y2 minus y3 equals 0. And hopefully we recognize geometrically what this is. This is a plane in R3. So that now gives us a way to describe what the span of that set of vectors is. Again, we've got these two vectors here that we were working with initially. The span of those vectors is described by this relationship here now. So let's rewrite our span in a form that has some meaning. So it's the span of the UV, that is. It's going to be the set of all y's, the vectors y, such that y is in R3. Again, we could just say that, or we could write out the generic vector y1, y2, y3. And we have the following condition that y1 plus y2 minus y3 equals 0. And that's how we describe the span of those two sets of vectors. So maybe practice that one and see if you can do that work on your own to determine the span of a couple of vectors.